Langchain Chroma Vector Stores. Description: Langchain Chroma Vector Stores are a powerful tool for building search and question answering systems. They are designed for storing and retrieving embeddings generated from text data, enabling efficient semantic search and retrieval. Chroma leverages the FICE library for efficient similarity search, enabling it to handle large datasets of embeddings effectively. Inputs: text data. The input text data that will be converted into embeddings and stored in the Chroma vector store. This can be raw text, documents, or any other textual content. Embeddings are numerical representations of the input text data, generated by an embedding model like sentence transformers. OpenA is embedding a P, or others. These embeddings capture the semantic meaning of the text. Outputs: vector store. The Chroma vector store stores the generated embeddings and their associated metadata. It can be queried for similar embeddings, enabling semantic search and retrieval. Retrieval results: when a query is made to the vector store, it returns a list of relevant results based on similarity scores. This allows for retrieving the most relevant information from the stored data. Steps: embedding generation. Input text data is first processed by an embedding model to generate numerical representations embeddings of the text. Vector store creation. The Chroma vector store is created and initialized with the generated embeddings and associated metadata. Indexing: the embeddings are indexed in the Chroma vector store using FICE for efficient similarity search. This allows for quick retrieval of similar embeddings during queries. Querying: when a query is made, its embedding is generated, and the vector store performs similarity search using FICE to retrieve the most relevant embeddings. Metrics: similarity scores measures the similarity between query embeddings and stored embeddings, indicating the relevance of retrieved results. Retrieval accuracy evaluates the performance of the vector store by measuring the percentage of relevant documents retrieved for a given query. Search efficiency measures the speed of retrieving relevant results from the vector store, typically measured in seconds per query. Visualization plots. Embeddings visualization. Visualizing embeddings in a low-dimensional space can help understand the semantic relationships between different pieces of text. Retrieval results. Visualization plotting retrieved results based on their similarity scores can help analyze the quality and relevance of the search results. Fine-tune parameters. Embedding model. Choosing a suitable embedding model can significantly impact the performance of the vector store. Different models have different strengths and weaknesses, depending on the task and dataset. Distance metric. The choice of distance metric influences how similarity is calculated between embeddings. Common options include cosine similarity and Euclidean distance. Indexing parameters. Parameters like the number of clusters and quantization levels in FICE can affect search efficiency and accuracy. Uncertainty methods. Confidence scores. Chroma provides confidence scores for retrieved results, indicating the likelihood that the results are relevant. Probabilistic retrieval. Incorporating probabilistic methods can provide more nuanced retrieval results, taking into account the uncertainty associated with embeddings and queries. Challenges and fixes. Challenge 1: memory constraints. Handling large datasets with millions of documents can strain memory resources. Sample use case that resulted in challenge 1: processing a large corpus of text documents with millions of entries resulted in memory exhaustion during embedding generation and storage. Fixes to challenge 1: utilize techniques like chunking to process data in smaller batches, reducing memory pressure. Explore memory-efficient embedding models that have a lower memory footprint. Utilize disk-based storage options instead of in-memory storage to handle larger datasets effectively. Challenge 2: Performance degradation. The performance of similarity search can degrade as the size of the dataset grows. Sample use case that resulted in challenge 2: performing search queries on a large vector store with millions of embeddings resulted in slow response times. Fixes to challenge 2: optimize indexing parameters in FIS, like the number of clusters and quantization levels. To improve search efficiency, utilize hardware acceleration techniques, such as GPU-based embedding generation and search. To speed up computations, consider using approximate nearest neighbor search algorithms, which trade off accuracy for speed. Challenge 3: scalability. Scaling the vector store to accommodate massive datasets can pose challenges. Sample use case that resulted in challenge 3: the performance and responsiveness of the vector store degraded significantly when handling a rapidly growing dataset. Fixes to challenge 3: leverage distributed storage and indexing solutions, such as Redis or Elasticsearch, to distribute the data and load across multiple servers. Explore cloud-based vector database services that provide scalable infrastructure for handling large datasets. Implement sharding strategies to split the dataset into smaller partitions, enabling parallel processing and querying. Challenge 4: embeddings quality. The quality of the generated embeddings can impact the accuracy and relevance of search results. Sample use case that resulted in challenge 4: using an unsuitable embedding model resulted in poor retrieval accuracy, with irrelevant documents being returned frequently. Fixes to challenge 4: carefully select an embedding model that aligns with the task and dataset characteristics. Experiment with different embedding models and fine-tune their parameters to achieve optimal performance. Consider using pre-trained embedding models specifically designed for the target domain or task. Challenge 5: data drift. As the underlying data changes over time, the stored embeddings may become outdated and less relevant. Sample use case that resulted in challenge 5: the vector store's performance degraded significantly after a major update to the underlying data, as the old embeddings no longer accurately reflected the new content. Fixes to challenge 5: implement mechanisms for regularly updating the vector store with new data and refreshing embeddings. Use techniques like incremental learning to update the model with new data without retraining on the entire dataset. Utilize data monitoring and analysis to detect changes in the data and trigger necessary updates to the vector store. Langchain Chroma vector stores. Chroma description. Chroma is a fast and scalable vector database specifically designed for embedding-based search. Langchain integrates with Chroma to allow you to store and retrieve information based on semantic similarity. This makes Chroma a powerful tool for building applications like question answering systems, document search engines, and recommendation systems. Inputs: documents. This can be a list of strings, text files, or any other format that can be easily converted to text. Chroma stores the text content of these documents and generates embeddings for them. Embeddings: Chroma uses a pre-trained embedding model to convert the text of each document into a numerical representation called an embedding. This embedding captures the semantic meaning of the text. Outputs: search results. When you query Chroma with a text prompt, it generates an embedding for the prompt. Then, it finds the documents in the database whose embeddings are most similar to the prompt's embedding. This allows you to retrieve documents relevant to the query, even if the query doesn't exactly match the text of any document. Similarity scores: Chroma provides similarity scores for each retrieved document. indicating how similar the document's embedding is to the query embedding. Steps. Embedding generation. Chroma uses a pre-trained embedding model like OpenAI's ADA embedding model to create embeddings for the input documents. This process transforms the text into a numerical representation that captures the semantic meaning. Vector storage. Chroma stores these embeddings in a way that enables fast similarity search. It utilizes an efficient data structure like HNSW hierarchical navigable small world to optimize retrieval. Similarity search. When you query Chroma, it generates an embedding for the query and compares it to the embeddings of all documents in the database. This comparison is performed using a similarity function, e.g., cosine similarity. Chroma then returns the documents with the highest similarity scores. Metrics. Retrieval accuracy measures how well Chroma retrieves relevant documents based on the query. This can be evaluated using metrics like recall and precision. Search speed measures the time it takes Chroma to perform a search query, indicating its efficiency and scalability for handling large datasets. Visualization plots. Embedding space visualization. This plot visualizes the relationship between different embeddings in a low-dimensional space, often using dimensionality reduction techniques like T-SNE. It helps to understand the semantic relationships between documents and identify potential clusters. Retrieval performance plot. This plot shows how the accuracy of the retrieval system changes with different parameters, e.g., number of retrieved documents. Similarity threshold. It allows you to evaluate the system's performance and identify optimal settings. Fine-tune parameters. Embedding model. You can experiment with different pre-trained embedding models, e.g., different OpenAI models, sentence transformers models to find the one that best fits your specific application. Similarity function. You can choose from different similarity functions, e.g., cosine similarity, Euclidean distance to adjust the way Chroma compares embeddings. Index parameters. Chroma offers parameters to fine-tune the HNSW index, impacting the search speed and accuracy trade-off. Uncertainty methods. Confidence scores. Chroma can provide confidence scores for the retrieved documents, indicating how certain the system is about the relevance of the document. This helps to understand the reliability of the results. Diversity sampling. You can adjust the retrieval algorithm to retrieve documents with diverse topics or perspectives, mitigating the risk of biases or overrepresentation of certain types of information. Challenges and fixes. Challenge 1. Embeddings can sometimes fail to capture subtle nuances of meaning, leading to irrelevant or incorrect retrievals. Sample use case that resulted in Challenge 1. A query about the capital of France might retrieve documents mentioning Paris but also documents discussing the history of the French capital, potentially missing the direct answer. Fixes to Challenge 1. Use a more advanced embedding model. Consider using a larger or fine-tuned model specialized for specific domains. Pre-process documents. Apply text cleaning and normalization techniques to remove noise and improve the accuracy of embedding generation. Utilize a combination of similarity measures. Combine cosine similarity with other measures like TF-IDF to account for different aspects of similarity. Challenge 2. Large datasets can slow down search speed. Sample use case that resulted in Challenge 2. A database of millions of documents might lead to significant retrieval times. Fixes to Challenge 2. Use a GPU for embedding generation. Leverage the computational power of GPUs to speed up the embedding process. Optimize HNSW index parameters. Adjust the index settings, e.g., number of neighbors, EF construction to improve search efficiency. Consider partitioning the dataset. Divide the data into smaller chunks for faster retrieval. With appropriate indexing for cross-chunk search. Langchain Chroma vector stores cosine similarity. Description: the cosine similarity method in Langchain's Chroma vector stores is used to calculate the cosine similarity between two vectors. It measures the angle between them, providing a score that indicates how similar they are. A score of 1 represents perfect similarity, while 0 represents complete dissimilarity. Inputs. Input 1 query vector. This is a vector representing the search query. It can be generated using a language model like embedding models from OpenAI or Hugging Face. Input 2 document vectors. These are vectors representing the documents stored within the Chroma vector store. They are typically created by embedding the text of each document using the same embedding model used for the query vector. Outputs. Output 1 similarity scores. The cosine similarity method returns a list of similarity scores, one for each document in the vector store. Each score represents the cosine similarity between the query vector and the corresponding document vector. Output 2 similar documents based on the similarity scores. The vector store can return a list of the most similar documents to the query. This allows for efficient retrieval of relevant information based on the semantic similarity between the query and the documents. Steps. Step 1 Query vector generation. The input query is first converted into a vector representation using the same embedding model used to create the document vectors. This ensures that the query and document vectors are comparable. Step 2 Cosine similarity calculation. The cosine similarity method calculates the dot product of the query vector and each document vector, dividing by the product of their magnitudes. This operation results in a value between 0 and 1, indicating the degree of similarity between the vectors. Metrics. Metric 1 Cosine similarity score. This measures the angle between two vectors, providing a value between 0 and 1, where 1 indicates perfect similarity. Metric 2 Mean average precision map. This metric assesses the retrieval performance of a vector store by averaging the precision scores for each query at different ranks. Visualization plots. Visualization plot 1 Scatter plot. This can be used to visualize the distribution of similarity scores and identify potential clusters of similar documents. Visualization plot 2 Heat map. This can be used to visualize the similarity between all pairs of documents in the vector store, highlighting areas of high and low similarity. Fine-tune parameters. Parameter 1 Embedding model. The choice of embedding model can significantly impact the performance of the vector store. Experimenting with different models and their parameters is crucial to optimize retrieval accuracy. Parameter 2 Dimensionality reduction. Techniques like principal component analysis (PCA) can be applied to reduce the dimensionality of the vectors, potentially improving performance and reducing storage requirements. Uncertainty methods. Uncertainty method 1 Confidence scores. By calculating confidence scores for the similarity scores, we can gain insight into the reliability of the retrieval results. Uncertainty method 2 Ensemble methods. Using multiple embedding models or techniques to generate embeddings can provide a more robust representation and improve the confidence in the retrieval results. Challenges and fixes. Challenge 1 Data imbalance. If the vector store contains documents with uneven distributions of topics, the retrieval results might be biased towards the dominant topics. Sample use case that resulted in Challenge 1 A vector store containing documents on science and sports, where there are significantly more documents on science. Fixes to Challenge 1 Implement techniques like oversampling or undersampling to balance the dataset. or use a more advanced embedding model that can handle imbalanced data. Challenge 2: semantic drift. The meaning of words can evolve over time, leading to potential mismatches between the query and document embeddings. Sample use case that resulted in challenge 2: a query for artificial intelligence might not retrieve relevant documents from the past that use different terminology. Fixes to challenge 2: regularly update the document embeddings to reflect changes in language usage and semantic meaning. Consider using techniques like transfer learning to adapt pre-trained models to the specific domain. Langchain Chroma vector stores maximal marginal relevance. Description: explain in detail maximal marginal relevance. MMR is a retrieval method designed to select a diverse set of documents while maintaining relevance to a given query. It works by balancing relevance with diversity, ensuring that the retrieved documents cover a wide range of perspectives and information related to the query. Inputs. Query: this is the user's search query, representing the information they are seeking. It's the starting point for the retrieval process. K: this integer determines the number of documents that should be retrieved and returned as a result. It controls the size of the returned set. Outputs. Relevant documents: this is a list of documents retrieved from the vector store that are considered relevant to the query. The order of the documents in the list reflects their relevance score. Diversity scores: each retrieved document has a corresponding diversity score that quantifies how different it is from the other retrieved documents. This score helps in ensuring a balanced and diverse set of results. Steps. Initialization: start by retrieving a small set of the most relevant documents based on their similarity to the query. Iteration: in each iteration, calculate the relevance score of each document in the vector store against the query and pay diversity score of each document against the already retrieved set of documents. Selection: choose the document that has the highest combined score, balancing both relevance and diversity. Update: add the selected document to the retrieved set and repeat the process until the desired number of documents K is reached. Metrics. Relevance score: this metric evaluates how closely a document matches the content of the query. It's based on the cosine similarity between the document's embedding and the query's embedding. Diversity score: this metric measures how different a document is from the documents already retrieved. It often uses a distance metric like Euclidean distance or cosine distance. Visualization plots. Relevance vs. diversity plot: this plot visualizes the relationship between relevance and diversity scores for each document. It can help in understanding the trade-offs made during the retrieval process. Document clustering. Clustering algorithms can be used to group similar documents based on their embeddings. This visualization provides insights into the relationships between retrieved documents and their overall diversity. Fine-tune parameters. Lambda: this parameter controls the weight given to relevance and diversity scores when selecting documents. A higher lambda emphasizes relevance, while a lower lambda prioritizes diversity. Uncertainty methods. Confidence intervals. By computing confidence intervals around the relevance and diversity scores, we can quantify the uncertainty in the retrieval results. Bayesian inference. This approach can be used to incorporate prior knowledge about document relevance and diversity, leading to more informed retrieval decisions. Challenges and fixes. Challenge 1: retrieving too many similar documents. Sample use case that resulted in challenge 1: when retrieving documents about a specific topic, the MMR might retrieve many documents that are very similar, leading to a lack of diverse perspectives. Fixes to challenge 1. Increase the lambda parameter by increasing the lambda parameter. The emphasis on diversity is reduced. And the MMR will prioritize documents with high relevance scores. Use more diverse embeddings. Experiment with different embedding models or techniques that capture more diverse aspects of the content. Challenge 2. Difficulty in determining optimal lambda. Sample use case that resulted in challenge 2. Choosing the appropriate lambda value for balancing. Relevance and diversity can be challenging and depends on the specific use case. Fixes to challenge 2. Experiment with different lambda values. Explore different lambda values and analyze the results to find the best trade-off for the specific use case. Use data-driven approaches. Develop an algorithm that can automatically learn the optimal lambda value based on the characteristics of the data and the desired diversity level.